talk, I have to inform you all these talks will be available on the web. However, I cannot see anyone in these in your departmental website. But I know some of these videos will be shown in the CTS. The website of the theoretical physics.
Center for Theoretical Sciences.
Yes, but the people who in charge told me maybe they will post on the YouTube. Okay, so it will be available. So once it is ready, we will inform you in SEMA. So everybody will be informed. Okay, then let me introduce the Professor Tsai. Professor Tsai actually is also one of our alumni. So he graduated in NTU in 1997, and afterwards he went to US for higher education. He obtained his PhD in chemical physics in the year 2005. And afterwards, he spent 2.5 years in UC Berkeley for his postdoc. Then, very shortly, he became our faculty members as a young assistant professor. And he was promoted to associate professor in year 2013. And then during this period, he get numerous awards. It's very impressive. He has his paper has been cited 4,500 times already. Okay, and he has a renowned two publications with more than 500 citations. All right. Then this.
I think one is 2,000.
Yeah. So the list is too long. So today he's going to talk about these frontiers in density functional theory and their applications to novel nanomaterials. So let's welcome Professor Tsai.
So thank you very much for the introduction, and it's my great pleasure to present my recent work in our department. And today I'm gonna talk about the new methods going beyond conventional DFT density functional theory and their application to nanomaterials. So here is the outline of my talk. So I will describe the importance of neuroscience, importance of DFT in computational neuroscience. Serial problems remains in constrained DFT, which is the conventional DFT, and our research directions and achievements. And more details will be focused on how DFT with fractional orbital applications and its extensions, and then apply the tau DFT to several novel nanomaterials, especially those with strong static correlations, which are regarded as challenging systems for conventional electronic structures. So these are the topics I'm going to talk about if the time is allowed. And the conclusion will be given at the end. And at the narrow scale, the quantum size effect of systems could yield new properties that are distinctly different from their molecular or bulk properties. Recent advances in neuroscience have led to several important applications. For example, materials for new energy, molecular electronics, like these figures, and quantum dots, electron dynamics. And yesterday we have a nice talk on this nano confined water presented by Professor Mao. However, there are challenges in computational neuroscience. There are typically more than thousands of electrons at the nano scale. For example, the C60 fluorine, which is a building block for carbon nanomaterials already contains 360 electrons. With current computing power, the many electron Schrödinger equation is, however, only applicable to a system with 10 electrons or less. At initial measure, for example, many body perturbation theory or the so-called green function theory are widely used in the physics community. And also the wave function theory widely used in the chemistry community, which could be applicable to a system with 100 electrons or less, remain very impractical for nanoscale systems. DFT density functional theory based on the Cone-Shine approach has been widely applied to study large ground state systems with a few thousand electrons due to its reasonable accuracy and computational efficiency. Let's say solving one electron Schrödinger equation with an effective potential is certainly much cheaper. So basically, this is the Cone-Shine equation that we need to solve. It's simply a one electron Schrödinger equation, and the effective potential is written as the sum of external potential, the Hartree potential, which is the functional derivative of this Hartree energy functional, and the exchange correlation potential, the functional derivative of exchange correlation functional. And the ground state density of the system is written as the sum of the square of the lowest n occupied Cone-Shine orbital. So when this set of equation is solved self-consistently, we will have the information of the ground state density law and also the information about the Cone-Shine orbital. Then we can evaluate the ground state energy of the system as the sum of the following four terms. The first term here is the non-interacting kinetic energy, and the second term here is the external potential energy, and the Hartree energy. And so the remaining unknown term will be the exchange correlation energy functional. So suppose the ground state density of the system can be written as this Cone-Shine answer, and we also have the exact exchange correlation functional. Then the theory itself, the Cone-Shine DFT, the theory itself delivers the exact ground state density and also the exact ground state energy. However, the exact exchange correlation functional remains unknown in terms of the ground state density law. If we write the exchange correlation energy functional as an integral over all space with exchange correlation energy density, and we make the following approximation for local density approximation, LDA and the GGA. And as you can see, the evaluation of the functional derivative of this term is much cheaper than the evaluation of the Hartree potential. Therefore, the computational cost of Cone-Shine LDA and the Cone-Shine GGA is similar to that of solving the Hartree equation. So it's even cheaper than solving Hartree equation. So that explains why the DFT with Cone-Shine approach can be applicable to nanoscale systems. And based on web of science, there has been an increasing use of DFT over the past 2 decades. So as you can see, this figure shows the number of papers containing the keyword of density functional theory plotted versus the year. And in 1998, the main developer, Walter Kohn, was awarded the Nobel Prize in chemistry for his development of the density functional theory. However, there are serious problems in conventional DFT, the Cone-Shine DFT. As the exchange correlation functional needs to be approximated, the accuracy of Cone-Shine DFT usually depends on how well EXC is approximated. I say usually is because there are also other factors like the representability of the ground state density in terms of the Cone-Shine answer, which I will talk about later. And while standard density functional approximation, DFAs, such as local density approximation and generalized gradient approximations, perform reasonably well for some application, they could also fail qualitatively for many others, as we will see later. Hybrid and the double hybrid functional, which incorporate non-local exchange correlation energy components into standard DFAs, are reliably accurate for a wide range of applications. However, a few serious problems remain unresolved. Therefore, the development of a generally accurate density functional for nanoscale nanoscale applications remains very important and challenging. To meet the challenge, our research has been focused on resolving the qualitative values of standard DFA, hybrid, and double hybrid functionals in conjoint DFT by developing new density functionals in case DFT and or new methods going beyond case DFT, while maintaining low computational costs for nanoscale applications. Our research can be highly interdisciplinary as our new method can be applied to both finite systems and extended systems. For finite systems are the common system adopted in molecular physics, quantum chemistry, and nanoscience. And extended systems are common systems adopted in condensed matter physics, solid-state chemistry, and materials science. So depending on what system you adopt, then you can study for different type of disciplines. But the theory remains the same. Okay, for small finite systems, we can employ highly accurate ab initio method. For example, full configuration iteration method, which is the exact method for given basis set. And also couple cluster CCSD plus T, which is a gold standard for molecule, small molecule. And for system with strong correlation, you can apply some kind of multi-reference method. And we can employ this highly accurate method to examine the accuracy of our new methods. Note that these methods are not applicable to extended system. And that's why we need to stay on finite system first to examine the accuracy of our new method before applying the method to nanoscale systems as well as extended systems. To show their applicability in computational nanoscience, our new methods are also applied for the study of various nanoscale systems, especially those with strong static correlation effects, which are regarded as challenging systems for conventional electronic structure method. It's challenging because the conjoint DFT with DFA hybrid and double hybrid functional are not reliable for systems with strong correlation. And the highly accurate ab initio method cannot be applicable for large systems with strong correlation effect. So there's no available theory for this system, and we want to resolve this challenging problem. And since this is a promotion talk, so here I show a list of my recent publications, including only those published after August 1st, 2013. So only those are published after promotion to current rank. So there are 15 published papers and one recent submission. So among the 15 published papers, 12 are published with my research group only, and 3 are published with my collaborators. And due to the time limit, I don't have sufficient time to talk all the 16 works. So I only have some selected work. For example, I won't be able to talk about a very nice work done by my former student, Chen Yuting, who is now a PhD student at Harvard Physics. And he performed a very nice and interesting work about the van der Waals interaction in real gas dimer when the interparticle interaction can be changed. And I also don't have chance to talk about the new density functional developed in conjoint DFT, like the number 2 and number 8. And I also don't have time to talk about the high harmonic generation that's done by Dr. Sun Xiaolin. I only will be focused on those marked in blue, which is about new methods going beyond conjoint DFT and their application to nanoscale systems with strong correlation. So let's start from this figure here. Here I showed why this multi-reference system are challenging system. H2 dissociation curve here. So H2 is only a 2-electron system. The reason I start from this system is because exact solution to Schrodinger equation is available because only 2 electrons. So then you can compare the accuracy of the other approximate method. So here The exact curve should go like this break curve, and this is the Hartree-Fock, and B3D is a popular hybrid functional, and we also have LDA, and PBE is a GGA, and these two are M062X and Omega B97X stage B are hybrid functional, and the B2 Bri is a double hybrid functional. So we have various kinds of functional in constrained DFT. And as you can see, while this functional in case DFT works reasonably well in this region where the single reference, the equilibrium near equilibrium separation, where the ground state wave function can be is dominated by single Slater determinant. So we call it a single reference character. And but they all fail qualitatively here. As you can see, you can get different answers from different functional, and none of them is correct. So and this is the region where multi-reference character become dominated. So multi-reference means the ground state wave function in this region is dominated by more than one Slater determinant. So only two important Slater determinant here, and that causes severe error, because this error is already comparable to the binding energy itself. So it can be regarded as a qualitative failure. So existing density functional in case DFT could fail qualitatively for multi-reference systems. Ab initio multi-reference methods are typically needed for studying these multi-reference systems. However, they are not applicable to nanoscale systems due to their prohibitively high costs. And to welcome this challenge, this challenge actually brings new exciting opportunity to work on new methods going beyond case DFT. So we need to have a look into the structure of constraint equation. So most people focus on the accuracy of change correlation functional, but in this work we focus on the representation of the ground state density. So this assumption may not be correct for every system, and as due to the effort of several researchers, lately Morrison, Ayers, and Young, some ground state density cannot be represented by this constraint answer. In priority lab, the exact change correlation functional can be indifferentiable at those ground state density. Barons and co-workers argue that systems with those ground state density can be multi-reference systems. Those are multi-reference systems are also called systems with strong static correlation. Therefore, we expect that a DFT associated with a ground state density represented by different ansatz can be useful for both single reference and multi-reference systems. So we focus on the representation of the density first, then ask what's the corresponding DFT associated with this representation. So what representation should we use? So we look at the exact ground state wave function. So exact ground state wave function can be obtained by the full configuration iteration method, full CI method, at the complete basis set limit. The full CI ground state wave function can be written as a linear combination of the configuration state functions obtained by Hartree-Fock calculations. And the linear expansion coefficient can be determined by variational principle. So we can apply variational principle to obtain this. And when we get the energy minima, that will be the exact ground state energy. The corresponding wave function will be the exact ground state wave function. So it's a way to solve Schrodinger equation exactly for given basic set. And then now we have complete basic set limit. Then that will be the exact solution to Schrodinger equation. And once we get the exact ground state wave function from full CI method, the corresponding density can be expressed with orbital and the occupation numbers. So the orbital here are the so-called natural orbitals, and the occupation number is the so-called natural orbital occupation numbers, which are the eigenfunctions and the eigenvalue of the one electron reduced density matrix associated with the ground state wave function of full CI method. However, the problem is that the computational cost for solving full CI method at complete basis at limit, it's just the cost for solving the Schrodinger equation exactly. So that means that we cannot apply this method to obtain exact density for system more than 10 electrons. So this is the main problem. So now, fortunately, from some quantum statistic paper published in Physical Review E, Fernbaugh and co-workers argue that the distribution of this occupation number in the so-called microcanonical average of strongly correlated fermions can be well simulated by the Fermi-Dirac distribution with renormalized parameters such as orbital energy, chemical potential, temperature associated with this Fermi-Dirac distribution. Then we think, since the representability of the ground state density is related to the multi-reference system, and we can also use Fermi-Dirac distribution to simulate the average behavior of the exact natural orbital occupation number. Then we ask ourselves, is it possible to formulate a zero temperature DFT associated with a ground state density with orbital occupation numbers given by the Fermi-Dirac distribution? And we address this problem in the JCP paper published in 2012. And we call the corresponding DFT as thermally assisted occupation DFT or tau DFT. So here is a simple picture here. So for physical system at zero temperature, where the electrons are interacting with each other via Coulomb interaction and are moving in the presence of an external potential, we are interested in the corresponding ground state density and the corresponding ground state energy. Now we consider another system, the reference system, at some finite temperature CDA, and where the electrons are non-interacting and are also moving in the presence of an external potential phi s. Suppose we can choose the phi s such that the thermal equilibrium density of this reference system equal to the ground state density of physical system. So basically, the assumption in tau DFT will be the ground state density of a physical system can be expressed as the thermal equilibrium density of non-interacting electrons at a given temperature CDA. And since due to the time limit, I won't be able to show the detailed derivation for the self-consistent equation that determine ground state density. So I only highlight the main theory that we applied to derive the equation. So we employ Holmberg-Kohn theory for ground state density functional theory, and the Mermin's theory for finite temperature density functional theory for physical and the reference systems respectively to derive a self-consistent equation for the ground state density and energy of physical system, because these are the information that we are really needed, we really want. And as you can see, tau DFT will be reduced to constraint DFT at CDA equal to 0. But in principle, we don't need to set the CDA equal to 0. And I will talk how should we choose the CDA later. And this shows the self-consistent equation that we need to solve to get the ground state density of physical system on tau DFT. So as you can see, we only need to solve one electron Schrodinger equation. And the effective potential is similar to the effective potential in constraint DFT plus additional term. That's the functional derivative of E-CDA, where the E-CDA is defined as the difference between non-interacting kinetic free energy at temperatures at zero temperature and that at temperature CDA. And the density will have the occupation number given by the Fermi-Dirac distribution. So the computational cost for solving this self-consistent equation in tau DFT is similar to that in case DFT. So we have similar computational cost as that of case DFT. And after this set of equations are solved self-consistently, we will have information of the rho and also occupation number Fi and orbitals. Then we can evaluate the exact non-interacting kinetic free energy by this information. So the first term here is the non-interacting kinetic energy at temperature CDA, and the other term here is the entropy distribution. And the ground state energy of the physical system will be written as the sum of these 5 terms. So as you can see, we need to make density functional approximation to both exchange correlation functional and also NTU-CTP, which are available in the literature for this one. And this one, LDA and gradient expansion approximation are available. Then the next question is that once we make this GGA, LDA or GGA density functional approximation, can the theory describe strong correlation or not? So let's look at this slide. This explains how strong correlation comes from tau DFA. Suppose for a range of theta, the full CI density, the exact density, can be approximated given by the density from tau DFA. We still have a degree of freedom to choose what theta should be adopted. That's the internal parameter. Suppose we choose theta such that the natural orbital occupation number are approximately described by the occupation number generated from tau DFA. That means from this equation, that means the natural orbital will be approximately given by the orbital generated by tau DFA. Of course, except for very high-lying orbitals. Because for very high-lying orbital, the Ni and the Fi will be 0. So it will be, the condition will be ill. So but for on the other hand, for high-lying orbital have vanishing orbital contribution. That means that even if they are different, they won't contribute to the density, and they won't contribute to the energy also, because you always multiply by this occupation number, which is 0 for high-lying orbitals. So it's this entropy contribution. So it doesn't matter this exception. So for kinetic energy of physical system, that can be written as this form exactly. That can be approximated by this expression because Fi simulate Ni and psi I simulate chi I. So you approximately can have this expression. This expression is just the non-interacting kinetic energy at temperature theta. So that's one of this term. So you also have this term here that can be absorbed into electron-electron interaction, because the free electron-electron interaction can be written as a universal functional of Holmberg cone minus the kinetic energy functional. So that means that even if we make density functional approximation LDA or GGA to both EXC exchange correlation function and the NTU-CTP, and the Hartree is only a mean field approximation. This 3 term will not be able to describe the fully non-local correlation effect given by strong correlation. However, this term is fully non-local in density, and we argue that this term could describe strong correlation. It's because this term will be insignificant for a single reference system. Because for single reference system, natural orbital occupation number are close to 0 or 1. So the effective temperature we should choose will be 0 or very close to 0. That means that this term vanish or very small. So it gives very small contribution for a single reference system. And it significantly lower the energy of system with strong correlation. Because for a system with strong correlation, the natural orbital occupation number for such a system will be fractional for active orbitals. Then the effective temperature theta will be larger than 0. Then this term will always give negative energy. That means keep lowering the energy of the system. And this conjecture is also supported by Collins' conjecture. Collins argued that correlation energy of a system is proportional to the so-called fundamental entropy evaluated by natural orbital occupation numbers. However, here in our theory, this term we argue this is to simulate static correlation instead of total correlation, and we also this form is also a symmetrized fundamental entropy in a symmetrized form instead of this form, unsymmetrized form. And to numerically verify our conjecture, we study again H2 dissociation where the exact results are available. And as you can see that tau LDA with